Our earlier programs on mathematical modelling have all involved applications of mathematics that have been developed quite recently. But now we're in a much more classical field, the application of mathematics to engineering. We're going to look at the mathematical models that arise when engineers design structures of all sorts. We're going to look in particular at cranes. You may have seen cranes like this around. Obviously, the major problem is to design something which is such that when you start lifting enormous loads here, doesn't cause the whole thing to topple over. In particular, let's take this thing here, which is a sort of stay to the crane. Now that will be anchored at its bottom end, and if we can find the force that is being taken by that stay, we shall then know something about the strength of the anchorage that we've got to get. Now, this crane has members, each of which is itself a quite complicated structure. And so the first thing we're going to do is to replace those by single rods. And so we get a thing like this. This is, if you like, the bare bones of the structure of our crane. And that's the thing we're going to analyze. Now, to help us with the forces involved in that, we've got a simple model crane in the studio. In fact, it's not an awfully useful sort of crane, this, because the weight is just hung on a fixed rope here and tied off on the end of the jib. But the jib is supported by this, and we can raise and lower the jib, and so raise and lower the weight. And with a swivel here, well, we could move loads with it over an arc somewhere over there. I've chosen this, though, because its structure is very simple to analyze. What are the forces involved in this? Well, there's first of all the weight here, and that is pulling down on the jib. And the jib doesn't collapse because of this stay rope here. That stay rope, in turn, is tugging at the top of this post here, and the force with which it's trying to pull it over is being taken by these two struts here, which are pulling down this way. So those are the forces, and to start the analysis, here's Graham Reed.
Well, this is a two-dimensional version of that crane, and the problem, as Stuart's just said, is to determine what the force is being exerted by this support on the base here. Now, we're going to make various assumptions, and the first assumption is that this structure is free to move, is freely pivoted. Like this. Let me show you. If I move this support and let it go, you can see the whole thing is free to move. Now, that corresponds to a structure which is so-called pin-jointed. In that case, here, for example, there would be a single force acting on the jib, and that comes in the analysis later. That's the first assumption. And the second assumption is that the weight here, being attached to the crane, is much larger than the various components of the crane. Now, the strategy that we adopt to do this analysis is to start at this end with the thing that we know, the weight being attached, and work our way round the structure until we get back to this end, the thing we want to know, the force being exerted by this support. Okay, then let's move on to the mathematical model. Well, here's our mathematical model, and you can see it's made up of lines, rather thick lines as it happens, because we want you to see what's going on. And let me attach the thing that we know, the force at that end. And in fact, I've chosen a force of 1, 2, 3 units. The arrow here represents the force in magnitude and direction. Now, we're going to analyze it, to start to analyze it anyway, by looking at the forces being exerted on the jib at this end. Well, I know there's another force. I know that the stay rope is exerting a force in that direction. I know its direction, but I don't know its magnitude. I also know that these two forces will combine together to give me a resultant. Let's suppose like that. So that's the resultant force at that end of the jib. Now, at the other end of the jib, you remember I mentioned a moment ago, there's another force like that. Now, you can see I'm in a situation here where I've got a body with two forces acting on it, and we know that one of our principles says that if you've got two forces like this, they must be equal in size, opposite in direction, and act along the same line, because the jib isn't moving. So we know that they look like this. They must be like that. So I know that the resultant force at this end of the jib is along the line of the jib. And I can use that fact, together with another principle, that is the principle of the parallelogram of forces, to determine the sizes of the forces at that point. We know the size and direction of this force. And we know the direction of this force, but not its size. From the parallelogram rule, we know their resultant will look like this. Different sizes for this force give different directions for the resultant. There's only one size which gives a resultant pointing down the jib. Okay then, so that's how it's done. But if you wanted to repeat that at home, what you would do is start with this force that you know and draw a line parallel to the line of the stay rope until you meet the jib, then a vertical line until you meet the stay rope, and that will tell you the size of this force, but more importantly, it will tell you the size of this force. In fact, I can see it's 1, 2, 3, 4, 5, 6, 7 units. So, if, for example, I put 3 tons on the crane, I would expect that there would be a force of 7 tons in the stay rope to hold that weight up. At least that's what the mathematical model predicts.
So, Graham's got us well into the process of mathematical modelling. He's abstracted the mathematical problem, which is to find the force here when we know the force there. And he's given us a method of solution, at least a partial method of solution so far, which enables us, by the simple graphical way, to find the force being exerted on the jib here and the force in the stay rope when we know this force here. In fact, he's worked it out for just one position. And you could do it for various other positions. For instance, down here, you'd have a parallelogram like that, and with the jib right up there, you'd have a parallelogram like that. And if you do this, you discover the way, for instance, in which the force in the stay rope varies, even though you've got the same 3 tons hung on there for various positions of the jib. But the position of the jib that he took was this one, and in this he said, if we've got a 3-ton weight on there, then the force will be 7 tons, which is being supplied by this stay rope. And the first thing that I'm going to do is a thing that you should do if possible with mathematical models, and that's to check out that prediction. Well, we can do that on our model crane in the studio. Here's our model crane, and I've also got here a means of measuring forces. It's really just a simple spring balance. Now, it's been calibrated, and you'll see when I weigh this thing on the end that we've carefully arranged that the calibrations match up to Graham's calculations there. And in fact, when I weigh that thing, look at the white stripes, it weighs 3 units. It's obviously not 3 tons, but it's 3 units. And I can find the force in the stay rope now if I simply hook that on there and then pull on this thing until, in fact, the real stay rope just goes slack. I've replaced the real stay rope now by this, and if you look now at what force is there, count the white stripes, 1, 2, 3, 4, 5, 6, 7, that's what he said, for 3 tons, 7 tons. So our mathematical model is indeed making the right sort of predictions at this stage. But of course, that wasn't the problem that we started out with. The problem that we started out with was to find the forces with which these are pulling on the anchorages. And that's quite a complicated problem because you've got really a 3-dimensional picture here. So I'm going to simplify it. If you imagine the forces in these two, then they are pulling down here. Think of the jib in the symmetrical position. Then they are supplying a force which could be supplied by a single stay down here. So I'm going to ask Graham in a moment to solve the thing with a single stay, because that is really now a two-dimensional problem, and there's no conflict now between that two-dimensional problem and Graham's two-dimensional diagram. So we'll let him go on with the analysis.
Well, you remember where I got to. A force of 7 units pulling on the jib in that direction. But you see, that stay rope also pulls on this upright post, and it's going to pull at this top end with an equal and opposite force of 7 units in that direction. You see, I'm gradually working my way round until I get to this support. Now, in addition to this force on this top end of the post, there's a force down this line of this support also acting on the post. Now that means I can apply exactly the same argument as I did before for the jib, but this time I'm going to apply it to this upright post. And if I do that, I should be able to find the size of this force. We know the size and direction of this force. And we know the direction of this force, but not its size. By the parallelogram rule, we can form their resultant. And the resultant must act down the line of the post.
So you see, using exactly the same method, Graham has in fact got us very near the answer to our problem. It's a bit like doing a crossword, this. Having got the answer there, you transfer that answer to there, and then you can get a better chance of solving the thing at that point, and indeed he's found that this should be 9 tons with the jib in this position. But of course, that's the two-dimensional crane. How does that help us when we've got a real three-dimensional crane? Here's the crane, which is in fact three-dimensional. And we've got 2 struts here, which are supplying force. They're supplying a force down here, whose value we've calculated to be 9 tons. Well, in fact, that force is in the plane of these two, so we're back to 2 dimensions, the two-dimensional plane being here. And all we've got to do, in order to find those forces, is to put that on there and ask that that 9 tons shall be supplied by these 2. And it's a simple parallelogram job again, in order to find the forces here and here, which are being supplied by these 2. And those, of course, in turn, are the forces with which they are pulling at the anchorages. In making up this mathematical model, we have in fact made a number of assumptions. The assumptions are to do with, first of all, pin jointing. Secondly, we assumed that the weight of the jib was negligible compared with the weight that was hung on the end of it. And then the method we used was a graphical method. Now, what about those assumptions and that method when it comes to real engineers? Well, we've got in the studio Mr. D.V. Edge from Wharton Cranes in Stockport. Their firm make cranes, and I'm going to ask him to make some comments on what we've done so far.
Well, the method of assuming pin joints is a perfectly normal one in calculating the forces involving the members.
So that an engineer would in fact assume pin joints, even though they might be welded or something like that.
Yes, initially he would consider that all the joints were pinned to establish the forces, and then later he may change his thinking in terms of loads which are not concentric.
His first assumption will be pin joints. Right. Now the second thing was this graphical method. Everybody thinks that everything's done by computer these days.
Well, I can assure you, Stuart, that everything isn't done by computer. The time and cost of programming in computer time is such that unless the problem was repetitious and involved a great deal of a designer's time, that the designer would resort to the simple solution shown by your graphical method.
So he would draw diagrams of the same sort?
He would draw diagrams exactly as you've drawn diagrams.
Yeah. And then perhaps the third thing, which was the assumption that the jib of this crane had a weight which was negligible compared with the weight to be hung on it. What about your engineers now?
Well, initially, he must assume weightlessness in order to keep the problem simple. In an engineering office, he would do one or two simple force diagrams in order to establish the load in the member, and from that, he would then determine the amount of metal required to withstand that load. Now, in doing that, of course, he has now created a method of calculating the weight, and he can then include that weight in future calculations.
So he starts with the assumption of weightlessness and includes the weight the second time round.
Second time round.
So, would you like to just make some general comment on what we've done so far?
Well, I think in summing up, I can say that the two assumptions of pin joints and weightlessness are the normal engineering assumptions until things start getting complicated. And the method of graphics, or as it's known in the design office, a force diagram, is a perfectly normal method used by the engineer on the drawing board.
Thank you very much. Now, that first crane that we analysed had severe limitations as a crane. Perhaps this model here looks more like a crane. It's got two ropes. One you can use to raise and lower the weight, and the other one to raise and lower the jib. And with a pivot here, you can cover a very big area, lifting loads from one place to another. Here's another version, exactly the same structure, and you can raise and lower the jib, and when you raise the jib, oh dear, just do that again. It looks as though the jib is all right when it's down there, but when we start raising it, then at some particular point it goes all unstable on us. And that's a very nasty thing for a crane to do, and so we'd like an explanation for that. I'm going to ask Graham.
Well, I think we can explain it, but before I do, let's make sure that you understand the problem. This is the old crane, you remember, with just the one supporting wire. The new crane has a rope attached there, over the pulley, and down. You wouldn't think that that would make too much difference, but in fact it makes quite a considerable difference. Now, we need to know something about pulleys before we can analyse this problem. This pulley at the top there is important. So let's analyse how pulleys behave. Well, here's a pulley, and around it there's a string, and on either side of the string I've got these measuring devices which will measure the sizes of the forces. You see this extension here, this white bit? It's the same length here as here, which means that the two forces are the same in magnitude. Now if we move this position, again, the forces are the same in magnitude, different from the forces we had before, but they're the same size. That length is the same as that length. And this is exactly the extra piece of information that I need in order to analyse this new crane. Let's look at the top of the jib again. This time there are three forces. One from the stay rope and two from the rope passing over the pulley. We'll look at the rope passing over the pulley first. The two parts of the rope exert two forces on the pulley. The force downwards is equal to the load. And we know that the force exerted by the other part of the rope must have the same magnitude, because the rope passes over a pulley. Now we can take these forces, which we know, and use the parallelogram rule to find their resultant. And here it is. This is the resultant force exerted by the rope on the pulley. And that's the same as the force exerted by the pulley on the jib. Now let's find the total force on the jib, the force from the pulley and the force from the stay rope. We don't know the size of the force from the stay rope, but But we do know something about the overall resultant. It must go down the line of the jib. And we can use this, as before, to find all the forces. But what happens if the jib is wound up to a higher angle? Well, let's do the analysis again. These are the forces exerted by the rope over the pulley. And this is their resultant, which again is the force exerted by the pulley on the jib. Now let's combine that with the other force on the jib, the force exerted by the stay rope, and look at the overall resultant. Whatever the force exerted by the stay rope, we can't get the overall resultant along the line of the jib. It's always tending to pull the jib upwards. The crane is no longer in equilibrium. It collapses upwards. Well, let's lower the crane again and watch what happens to the forces as we wind the jib up. This is the critical position. Any higher and the crane collapses. The critical position is when the jib bisects the angle made by the rope around the pulley.
Well, I don't know about you, but I found that explanation very satisfying. That rather wild behaviour of our little crane there is predicted by our simple mathematical model. In fact, we've got a quantitative prediction. What was it? That it will go unstable when the line of the jib bisects the angle between the two strings. Off we go, winding this up, and it's at about that point that it goes unstable. And if I just push it back into position where it went unstable, look at the line of the jib and the angle made by the two strings. Not a bad prediction, is it? So, our mathematical model has in fact given us an unexpected prediction, I think. Now, as with all mathematical models, you could go on refining the thing and taking into account those initial assumptions and perhaps modifying them and so on. But think of a crane designer. He's never going to be designing a crane to lift, say, exactly 20 tons. Although he'll put a maximum 20 tons, he'll build a bit of extra strength into it. He wants an estimate of the size of the forces. And this sort of mathematical modelling is quite adequate for that. And I think we've learnt one other thing. If you ever do see a crane like this with a very short jib, then I think the best thing is to keep out of its way.